folks, hold up your mini whiteboards. I want to see what you're thinking at this point. Okay. All right, so we've got some y-intercepts. We've got some curves going uphill in some way. We've got some with gradients that decrease with time, or decrease with x. Well, I've got my lines up here. So what coordinates do we definitely know for this curve?
Y-intercept.
We know the y-intercept. Because when y equals e to the x, it intercepts at e to the 0, any number to the power of 0 equals 1. So it intercepts there. Now, would it ever intercept the x-axis? What do we think? What would that mean? Well, it would intercept the x-axis where y equals 0. So, let's say we set y equals to 0. So we've got 0 equals e to the x. Now, what value could x be? Any ideas? I mean, if we had x equals minus 2, then e to the x would equal 1 over e squared. Do you remember that power of the thing? We can have negative powers, we can have positive powers. So what value of x could we have that means that this is very, 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 very small? Infinity. So if we had e to the power of negative infinity, that's basically 0. So when x equals negative infinity, our curve finally crosses the x-axis. So if I be silly and extend it a bit to negative infinity, that's where our exponential curve would finally cross the x-axis. So we know where it crosses the x-axis, we know where it crosses the y-axis. Now, I'm going to erase that because that will never be on one of our graphs. You know, we'll never get down that far. Now, for our curve here, it only crosses the x-axis at one place, negative infinity, okay? It never crosses anywhere else. That means all our y values are positive. So if all our y values are positive, our gradient has always got to be positive too. So our gradient will always be increasing, going upwards and upwards, higher and higher as x increases. So as a sketch, we start off really small over here, we go higher and higher and higher, go higher and higher and higher. You see the gradient is always increasing with x. Now I can plot a much nicer one for you on autograph. Can you have a sketch of that in your notes, please, while I bring up autograph? And I'll show you the neat version of it. This is quite pretty. So, folks, I'm sure you've got a sketch down. This is what it looks like when a computer plots it. Okay? Starts off really small, but still positive. It keeps being positive. The gradient keeps increasing as x increases. It gets steeper and steeper and steeper. It never gets to an asymptote, though. It's not like a tan wave. It never gets to an actual asymptote where it gets infinitely steep. That only happens when x is infinite and it's off our graph. So, the general shape that we always draw for an exponential is always this kind of shape, which happens to have a y-intercept of 1. So, I'm going to jot down some bullet points of important facts that you've got to remember about this graph, and they come in handy. So, y equals e to the x always has a y-intercept of 0, 1. Y equals e to the x always has a positive y value, even if it's really small. Y equals e to the x never intersects the x-axis except at negative infinity. So, jot that down as facts. We'll be using these facts to future time. And to be fair, there's quite a few exam questions which go, sketch an exponential curve. So if you knew these facts off by heart, you can reconstruct what the curve looks like, even if you don't have a strong visual memory of it. Now, we're going to have a little look at logarithms again. And logarithms that happen to use e this time. Now, in the past, we've had things like y equals 10 to the x, and then we could take log to the base 10 of both sides. Rearrange things as we go, using our log rules, using our log laws. So, we can bring that power of x down, so we can end up with log 10 of y equaling x lots of log to the base 10 of 10. So, Dean, what is log to the base 10 of 10?
1.
1, yeah. So, don't need that bit. So we can rearrange things like that. Now, let's bring up something. Let's bring up an inverse function for a sec. Okay? This is just a function which does the opposite thing to your values. So, for instance, a function processes value a into value b. The inverse function would process value b into value a. So, a function of a could equal b, and the inverse function of a should then equal a. Like, for instance, the square root of a equals b, let's say. So, how would I get from b to a? What would I do to b?
Square it.
Square it? So b squared equals a. So the square root is the inverse of squaring. Squaring is the inverse function of square rooting. Okay, it's got that kind of connection. Now, the reason why I'm bringing this up is because we are going to look at the inverse function of e to the x. Now, what's the inverse function of y equals e to the x? Well, you can think of it like this. I'm going to sketch a little thing for you. It's a graph. Now, this is y equals e to the x, okay? A very easy way to find out the inverse function of anything that you can plot as a graph is to take a mirror image of it. Now, if I plotted the line y equals x, I can take a reflection of y equals e to the x like that, flipping it diagonally. So, now we've got something that looks a bit like that. This is called the natural log of x. Okay, so this green line is y equals the natural log natural, if you're French, of x. Now, you can kind of see this because if you picked a particular x value, like that one, and you went up to the y equals e to the x line and went along to get the equivalent y value, because we're dealing with mirror images here, if you then took that y value and went along to the mirror image line, we should get that answer back. Okay, it's just like going in different directions. We can go that way, or we can go that way, to go between the x and y values. Now, the lucky thing about this is that this is just taking log to the base e of x. It's just an extension of that idea with a slightly different name as a shorthand. So, if we had e to the x equals y, we could take log to the base e of both sides. Now, that is just log to the base e of y. That would equal natural log of y. Okay, that's just a shorthand we have for log to the base e. Now, on this side though, we've got log to the base e of e to the x. So what power of e would give us e to the x? Any ideas? Amy, what do you think? What power of e would take us to e to the x? Not sure. Well, e to the power of what will equal e to the x? X! That's literally it. So, remember, a log is asking the question, what power of the base number gives us our answer? In this case, it's just x. So we've got x equals the natural log of y. So we have this lovely relationship between them that you can find visually or find by using the logarithm laws. Okay, so I would love it if you guys could write this out for me in a way that you'll remember. Okay, so you might want to bring up that thing to remind you where the x comes from. And we've established a new function as well. It's called the logarithmic function. Hello, Alan. He's gone. Dismissed. Now, what I'm going to ask you next, after you've made notes, is to actually sketch the natural log function. Now, you've got to be very careful sketching it, which is why I'm asking you to do it. Because y equals e to the x obeys certain rules that we know already. we can reuse certain facts about it to sketch our logarithmic function. So after you're done writing this up, get out a mini whiteboard and give it a shot of maybe writing down the facts that the natural logarithm function would use. So look back at the exponential function facts. A lot of them you could reuse because logarithmic function is just a mirror image. So you just have to flip certain things around, certain x things, certain y components, things like that. So if you had to go at sketching, I'd like you to show it to me so I can go, at it, at it, at it. Okay. Now George, what do you think the x-intercept is of the logarithmic function?
1.
Okay, that's good. Now, how did you think that?
I just take something out the top of my head and just take a rough guess, to be honest.
Okie dokie. Fair enough, guessing is sometimes helpful. Now let's think about y equals e to the x again. Y equals e to the x has got a y-intercept of 0, 1. Do you remember? It intercepts because e to the power of 0 equals 1. So that's our intercept for y equals e to the x. Now, if we had y equals log of x, it's a mirror image of this. So if I put on a mirror image line, like that, that point has got a mirror image there at 1, 0. So instead of having a y-intercept, we've got an x-intercept now. Now, think about the general shape of our e to the x curve. It looked quite like that. I'm going to write it a bit like that, okay? So, if we take a mirror image of it, it's going to be a curve, but instead of an always increasing gradient, we've got always decreasing gradient. It'll be a mirror image. So I'm going to try this freehand, folks, but it'll always be like that, okay? A mirror image like that. Notice how it doesn't cross the y-axis, just like this doesn't cross the x-axis. Now, you might think I'm done here, but I'm not, because y equals e to the x always has a positive y value, okay? Y is always greater than 0. Now, you might think this isn't a problem because this current curve always has a positive x value as a mirror image. Unfortunately, we can only create our inverse function from y values that are produced by y equals e to the x. So e to the x produces all of these lovely positive y values, and so y equals natural log of x can only have positive y values. So this bit here doesn't exist. Those y values are less than 0. So our natural log curve here is positive y values with an intercept of 1, 0, and it's a curve that's always got a decreasing gradient. So, we have got 3 facts once again. We've got the intercept, the fact that we can only have positive y values, and the fact that the gradient is always decreasing, instead of the exponential function where it's always increasing.